Hi. In this section, we're going to review the multiplication rule and the addition rule for probability. And so we discussed the differences between the multiplication rule and addition rule in the sense of disjoint and mutually exclusive and independent slash dependent events. And so we just want to recall that when two events are mutually exclusive, that means there's no overlapping outcomes. Whereas independent events mean that the following event isn't affected by the first event. So let's go ahead and take a look. So the first thing we want to look at is the multiplication rule. And so the multiplication rule is derived by the conditional probability. So recall in the previous section, we had said that the probability of an event occurring given an event occurred was equal to the probability of A and B occurring all over the probability of the first event. Now we did this with the contingency table with gender by the hand they write with. And we said, okay, what's the probability that a randomly selected person is a woman given that they are right-handed? And so that's where this formula came from prior. But then they were like, okay, so let's just multiply each side because probability, remember, is just like a decimal or a small fraction. And so we can go ahead and multiply each side by this denominator and clear denominators. And when we clear denominators, we end up getting this other formula that's super cool for the probability of A and B, and that's just equal to the first probability of the first event occurring times the probability of the second event occurring given that the first event had already occurred. So this is how we get now this conditional probability formula, which is really the multiplication rule, and it's generic. So sometimes you're going to have independent events and sometimes you're going to have dependent events, but this rule works for any type of events, which is really nice. So it's one rule for all. So it's nice. So it's pretty good. And then I just want to note that, again, this goes with the word and. And again, this works for any type of events. Okay. Okay, so essentially all you're going to do is still multiply, right? So it's still multiplication with the word and. Okay, and then we just check to see if they're what type of events they are, independent or dependent. So let's try this first example. So the first example states to consider Bucky's deck of cards and his friend Satchel. And if we recall from previous examples that Satchel or Bucky had a deck of 52 cards standard, and he always had Satchel draw a card, right? So what is the probability of Satchel drawing a heart without replacing the card and a spade? So now, if we read that, this phrase here, without replacing the card, should be the red flag that says these are dependent events, and that the second event will be affected by the first. So here, if we identify the events, A, where that's the first event of drawing a heart, and then the second event, call it B, is when Satchel needs to draw a spade. So the probability of Satchel drawing a heart and a spade is equal to the probability Satchel drew a heart times the probability Satchel draws a spade, given that Satchel drew a heart in that first draw. And so this is him drawing the heart, and then the spade. But because now that we know that these are dependent events, we know something's going to change on that second fraction on the probability, right? So what is the probability that he draws a heart? Well, we had discussed this many times that any one suit is 13 out of 52, right? Or 1/4 times, and now what we're going to get is, okay, well, now how many spades are left in the deck? Well, if he drew a heart by chance on that first one, how many spades are left in the deck? Well, it's a suit, so all 13 are left in the deck, right? But how many cards were left? So he drew a heart on the first one. You had 52. Now he draws one and is holding a heart. There is one less card in the deck, and there's 51 cards. So just because there were still 13 spades in there doesn't mean that there were less cards to pick out of, right? So it changes this denominator right here. And that's where the dependent events come in, right? Because we know the probability is going to change on that second draw. Okay, and if we were just to put this in our calculator, we could easily go to our calculator, and I can just put 13 divided by 52 times 13 divided by 51, and we'll get 0.0637. Okay, which is also 6.37%. And if I wanted this in a fraction, it usually will give us a fraction by hitting the math button and hitting 1. If it's sometimes too much for the calculator to handle, it won't give the fraction. But if it can handle it, it will give you this nice reduced fraction. We'll see in a future section when the fraction is just too big and too large of a denominator for it to convert. So 13 over 204. So it just depends on which answer you're required to write. So just check with your instructor. Okay, so let's do another example. Consider Bucky's deck of cards and his friend Satchel. What is the probability of Satchel drawing 2 clubs without replacement? So now Bucky has this deck of 52 cards, and Satchel's just going to take 2 out. So this is going to be the event will be drawing a club, right? And once again, we see the words without replacement, and that's our red flag to tell us that we have dependent events. Now, when we have dependent events, remember what this means. This means that the second probability will be different than the first, right? Something happens in the first event in which will change the following event. Okay, so if we wrote this out, we would have the probability of Satchel drawing a club and another club. Well, that's just equal to the probability that Satchel draws a club on that first event times the probability that Satchel draws a club on the second draw, given that he already drew a club in the prior draw. So this is, oh, I'm not good at drawing, but I'll try. There's the club. They just look like a tree now. Okay, now we know if I wanted to highlight to see that the dependent events means that this second probability will be different. So what's the probability that Satchel draws the club on the first draw? Just as you have 52 cards, draws, well, that's a suit, and so that's the same as usual, 13 out of 52. Times the probability he's going to draw a club again on that second draw, given he already drew a club. Well, let's stop now. Now it's a little bit different than the prior example. So he has the deck of cards on the first draw, and he draws by chance a spade. Well, if there's 13 spades in the deck total and he takes one, how many spades left in the deck? Not all 13, right? He has one less, which is 12. And he also is already holding that club, which means on the second draw, not only is there 12 clubs left in the deck, but also only 51 cards left in the deck. So not only does that denominator change, but in this case, both numerator and denominator change. So it's not just one size fits all for this formula. All we know when we have dependent events is that the following probability is going to be different. And that's all we know. And every following probability will change on the problem itself, the intent of the problem, and so on. And so you can see that the fractions are quite simple. So we can go ahead and put that in our calculator. It's going to be a little different now, right? Because here we have 13 divided by 52 times 12 divided by 51. And so we can round to 4 decimal places, 0.0588, which is 5.88%. Okay, and then if we wanted the fraction, we could go to math and hit 1 and see if it'll give us the fraction, which is 1/17. Okay, so again, in the format in which we write our answer, whether it's a decimal, a percent, or a fraction, is really up to the discretion of the problem and your instructor. So some problems in your homework will have it round to the nearest decimal, round to the nearest percent, or give your answer in a reduced fraction, and you just have to read the problem carefully. And with dependent events and the multiplication rule, we always assume without replacement. In the real world, we do not replace things. Like we just don't. And even when we have a deck of cards and we're playing blackjack or poker, we don't replace the cards once we get 5 cards for poker. We don't say, "Okay, give me the deck back. Let me put them back." No, you hold on to them. So we always assume without replacement. In fact, it's only when it states that it's with replacement is when we actually have the other formula of the non-conditional probability. So we always use this multiplication formula with probability more likely than any other multiplication formula for probability. Okay, let's try an application. So this is actually taken from this data is actually taken from the National Data Information Center. And so this in 2005, 19.1% of all murder victims were between the ages of 20 and 24 years old. Also in 2005, 86.9% of all murder victims were male, given that the victim was 20 to 24 years old. What is the probability that a randomly selected murder victim in 2005 was a 20 to 24-year-old male? And round to 3 decimal places. So this is a lot, right? So we just want to make sure, and I always like doing like a little appendix as you've seen in these last 2 examples, and write some stuff on the side and organize my information. So let me go ahead and do that. I think the first thing I want to acknowledge is that 19.1% murder victims were between the ages of 20 to 24. The second piece was that 86.9% were male, and then you can see the important phrase here, given that the victim was 20 to 24 years old. So now what they're saying is they have all these murder victims, right, between the ages of 20 and 24, and so now they're saying, well, if we have all these murder victims from all age groups, only look at 20 to 24, take your hand, grab somebody out of that 20-24 age, and what is the probability that that person I grab is male? And so that probability was 86.9%, right? So let me write it in red. Given the victim was 20 to 24 years old. So I think this is the real important part when we're going to interpret this in terms of the formula. So now, if I have the probability of the events A and B, right, that's going to be equal to the probability of A times the probability of B given that A has occurred. So let's write this out. What is event A? The first event would be that the victims were 20 to 24-year-olds, right? And the second event, let that be the victims that were male, right? Okay, so here we're going to have the probability that they are 20 to 24 and male is equal to the probability that they're 20 to 24 years old times the probability that you're male given that they're 20 to 24 years old. Okay, so we can see that we have some pieces and then some pieces are missing. So let's just fill in. Well, we have the all murder victims between the ages of 20 to 24, right? Which was 19.1%, 0.191, times the probability that we have a male given to be. So now you're only looking at this little set and you're putting your hand to grab a male, and that was 0.869, which is pretty high. Can you imagine all the murder victims? So people who were murdered in the year 2005 between the ages of 2024, so young, and the probability that I go randomly select somebody is almost 90%. I mean, that's just really sad, right? Okay, so if I just take these two and multiply them, and I can do that in the calculator, 0.191 times 0.869, we get 0.165979. And this could be interpreted as 16.6%, right? And if we wanted to see a fraction, we could try to go back to the calculator and interpret this as a fraction by hitting math 1 frac, and then notice it doesn't give it to us as a fraction because it's just too much for the calculator to compute. So sometimes it won't compute the fraction. But in real life, when you're working for the data source, especially national, because there is a data mart and mathematicians work there, they don't really use fractions. They do use the percentages as they were given inside the report. So what would we say about this? So let's write something. We would say that there is a 16.6% chance that a randomly selected murder victim in the year 2005 was or is a 20 to 24-year-old male.